Okay, so the first part of the class, again, okay, we are reviewing linear algebra. Okay, and why do we do linear algebra? Okay, because we want to manipulate a whole bunch of data at once. And the most efficient way to do it, instead of writing like, this multiplied by that, you just write the whole vector and you just multiply the whole vector by a number. Okay, you multiply a whole vector by a row vector, you multiply a whole vector by a matrix. So you can manipulate a whole bunch of numbers at once. Okay, by manipulation, sometimes it refers to solving a whole bunch of equations simultaneously. Okay, and because mathematicians have been playing around with this matrix, okay, you get to analyze large number for property. Okay, i.e., okay, determine whether the system of equation has unique, none, no, or infinitely solution. Even before trying to solve it. Okay. Now this is only one example. This is one example of analysis. Okay. Now this analysis is called determinant. Okay. Determinant with determinant. With determinant. Determinant. Okay. With theory. With their theory. You can tell so that's that. Okay. And for linear algebra, because so those are the 4 reasons why you study linear algebra. And those are the 4 reasons, 4 ways you use. Okay. So you use linear algebra because basically you can think of it as a mathematical representation of your database. You manipulate a whole bunch of numbers at once. And that's, remember, you are doing big data. Okay. You can solve a whole bunch of equations. Instead of whole bunch, I just say system of equations. Okay. In fact, the word simultaneously is redundant. Obviously, you solve a whole system has to be simultaneous. Okay. With matrix theory, you can also analyze large numbers data for properties. In particular, example, with determinant theorem or something observed, you can tell whether or not in front of you have unique or no or infinitely many solutions even before you attempt to solve it. Okay. And then, of course, with matrix theory, you have other things. You have other things. You have other things. Okay. For example, something else with linear regression. Now, some of you may know this, some of you may not. we analyzed what's called multi-collinearity, or solve, get the coefficient. So, you know, plenty. I mean, it's so many of them. Now, finally, because data analytic techniques, statistical method last year, machine learning this year are based on being able to manipulate a whole bunch of numbers. Okay. You will. Okay. So that's why linear algebra. Now, the last time, sorry, the case that I was showing you, this situation, why calculus? Okay, why calculus? Okay, why calculus? I'm gonna start from one answer. Let's go to number 2. Okay, notice that when you had infinitely many solutions, okay, you have infinitely many solutions. Your job is to find the one that is somehow best with respect to kind of criteria. Okay? This means you want to maximize. Okay? So this thing that you saw earlier here shows up here as well. But I'm not going to talk about it yet. I'm talking about rate of change. So what's calculus? Calculus allows you to analyze how quantity changes. Okay? In other words, if the world stands still, you don't need calculus. Okay? If the world changes at constant rate, you also don't need calculus. Now, what do I mean by that? What do I mean by that? Okay? If you grow 1 centimeter each year, okay, you don't need calculus in the general sense. Why? Because when you are born, you have 0 length, or you start with have 0.5 meters, and then plus 1 centimeter for every year you get older. Okay? So there's no point in studying anything in between. You can just draw a line. You start with this height, and every year you grow a little bit taller. You never stop. Okay, so it becomes a straight line. Okay. Now, if I did this, watch what happened. Oops. Okay. It doesn't matter how many times I did this. the slope will be the same. The slope will be the same. The slope will be the same. Okay. In other words, it's very simple to analyze. Okay. If you wait a little bit, you grow a little bit. If you wait a long time, you grow a long time. And it doesn't matter whether or not you're young or you're old. You have 1 centimeter of height added to your head, or added to your height for every year. Okay. So this is the same. Okay. So you grow at a constant rate from when the day you're born to the day you die. Okay. Let me ask you a question. How many people grow like this? None. Nobody does. Nobody does. Nobody grows like this. So what's going to happen is, this is what you look like. You grow. Maybe you have a growth spurt when you and maybe you shrink a little bit when you get older. So the rate of growth here versus, okay, the rate of growth here versus the rate of growth here versus the rate of growth here are very different. Okay? This is what we mean by instantaneous rate of change. Well, it's not quite instantaneous because this is still y, right? So what calculus want to do is, how about if I want infinitesimal? How would I do that? How would I do that? Well, the way I would do it is, say, at this point, I just draw a tangent line, and then I measure the slope of that. The slope at this point is the same thing as the slope at that point. The trick is to find this line, because this line changes, right? Yeah. So that's where calculus come in. Okay. Now, calculus allows you to analyze how quantities change. Differential calculus, I'm just going to write the name first, allows you to calculate rate of change. 3. Integral calculus allows you to calculate accumulate changes given. Now, I want you to get this. I want you to get this. Now, mathematically, fortunately, you don't have to do this yourself. So let's go to my mathematical sheet. Okay. So this is going to be the concept that we talked about today, but I demonstrated again with a more example. You will have this. You have this to play with. Now, differentiation is to find the rate of change. Now, let's go to calculus. Let's see what calculus does. Okay, so differential calculus. Say, what if you have y is equal to f of x, but y is not linear function? Okay. So now this is gonna make you a little bit confused now. I just told you that a whole bunch of things in life can be handled with linear algebra. Now I'm saying that, well, that's only a special case of how things change in life. But that's precisely what happened. How things change in life in linear way is only a special case, right? Special case. So it's quite rare. So in real life, not only do you have all kind of complication above, you also deal with nonlinear function. Now, you want changes in y for very, very small changes in x. Okay. Now, if f of x is mathematical function, you can calculate what's called derivative of f. Now, I'm going to show you, now this is where the power of Mathematica comes in. You don't have to do this thing yourself. Where are we? Where are we? Okay. So if I have a really funny looking function, okay, I have a funny looking function. Now I'm going to be a terrible person. I'm going to give you a really difficult function to look at. So this is my function. Okay, this is my function. This is my function. Plot. Okay. X from say 1 to 10. It's 0 to 0. Okay. Now, this is some function. How am I going to be able to find the slope of this? Now, around here the slope is 0. Around here the slope is negative. Okay. Mathematica allows you to do this by giving an expression. Take derivative of this with respect to x. That's it. Now, this function, it would take you maybe half an hour to come up. Well, it would take you maybe 5 minutes. But you can imagine that I can make this more complicated. Just like I show you a simple case in 2 dimensions, and I told you in real life you will have thousands of variables in so many dimensions. Likewise here, the function can be complicated, can be even more complicated. Now let me plot this side by side. And you will notice something. Again, I want you to get the intuition. You don't have to do it because Mathematica does it for you. See? This is the original line. This is the value of the slope. So right here, from the get-go, for every 1 unit increase in this way, you get 1 unit increase that way. So the slope is 1. Yeah. Let me draw a line. Let me make it look nicer. Yeah, let me draw a line. See? Oops. Okay. See that? This is the slope, is 1. How about here? What's the slope? 0. How about here? What's the slope? It's negative, but not quite 1. And the slope stay pretty flat, right? In fact, it becomes less negative. And it doesn't matter what function I put in. Okay, I can put in something log x. I don't know. Okay. Now make sure I put this in here. Oops. So that's even funnier. This function doesn't even converge. Okay. So the point is you can give any function, and it will give you the slope. Okay. Now, so differential calculus In Mathematica, you just type d of f of x, yes. That's it. So all I want you to do is to say that if y is equal to f of x, then derivative f prime of x gives you rate of change. Okay, instantaneous rate of change. Now, conversely, if I have let's go back to this equation. Okay, let's go back to this equation. Let's I'm going to plot this function. Okay. Okay. So let's say I'm going to make this function. So let's say this is the rate of change. So this could be time. So let me go back. What is finding derivative? Finding derivative is like division, right? You take the height, divide by the width, but you make the width small. Okay. Think of derivative as dividing height by width, width going to 0. That's a good intuition. Yeah. So we have this thing. You have height divided by the width, but it only at this point. So you have to make the height of the width and the width very tiny. Okay. So you're dividing. The differentiation is dividing height by the width, but you're dividing something that's getting close to 0. Now, integral calculus is like trying to multiply width by height, but height changes. Okay. So if I have a curve that looks like this, yeah, if I have a curve that looks like this, and I want to say from here to here, what's the area? The area is this, right? It's the width times the height. That's easy. Okay. So if the width is time and the height is speed, width times the height is equal to distance. Right? The point is, what if your speed is not constant? What if your speed looks like this? You start from 0, you speed up, you slow down, you go backward, you go speed up again. My question is, I want the area under the curve between here and here. So I want this area here. I want the width times the height, but the height changes. How will I do that? Well, this is where integral calculus comes in. So if I have this area, so where was the example? Okay, let's say this is my, Now I want to know what the area between here and here is, between 1 and 2. Okay, I can do this. Integrate. Okay, integrate this function here. I want between, what is it, 1 and 2? It gives you some value. Now, I don't know what that is. Numerically, it's giving you something like 99. So area between 1 and 2 here, this block here. Okay, so between 1 and 2 here, if I draw a line, I want to find the area here between 1. What's my one? What's my notation? Sorry, my bad. Okay, but okay, there it is. Okay. Yeah. So if I want the area here between 1 and 2, okay, this area here. I'm not drawing very well. Sorry about that. Okay, but that's what the area comes down to. So how does this help you? How does this help you? Well, let's think about it. Okay. Now, think of PDF, probability distribution. Okay. Your CDF, cumulative distribution function, is actually an area under PDF. So to calculate probability A less than X less than B, where X has distribution F, you just integrate function F X between A and B. So let's go back to our example. Well, actually, we don't have. I can just show you. It's very easy. PDF normal distribution, say 3 and 4. Okay. And I'm going to plug underneath it CDF. Okay. X between 0 and 7. See? So this is
Adam, can you go up a little bit? Thank you.
All I want to show is that PDF, if you think of PDF as a function, that's the blue one here, right? Okay, let me make it smaller. There. If you think of PDF as the blue one here, right? The blue one here. As you go from here to here and you accumulate the area, the probability that x lie between 2 and 3 is the area underneath the blue curve, right? Probability that x lie between 2 and 3 is the area underneath the blue curve. Is equal to the integration from 2 to 3. Now this function is the integration. So the area between 2 and 3 is equal to this point minus this point. So this width here will be your probability. And if you think about it, this is your probability distribution function, right? The blue one here. The yellow line here is the accumulated probability as x go from minus infinity to plus infinity. So obviously x has to be somewhere, right? Probability distribution function. So what's the total area of the distribution function? 1. So the CDF, that's the yellow line, has to go from 0 to 1, right? Now, you want to know what's the probability. Yeah. So what's the probability, right? That x is less than equal to 3, 4. Say what was it? 3 and 4, right? 2. Okay. Where x is normal distribution. What is it? 3 and 2, right? 3 and 1. Okay. Now it's going to give you something that you don't know what it means, but I'll give you the number. 0.34. Let me say that again. X is normally distributed with mean 3, standard deviation 1. So that's PDF. Center at 3, and the Napoleon cap has the brim at 1, plus minus 1. So that's the blue line here. Okay. I want to know what's the probability x between 2 and 3. Well, that number comes up to this. Okay. Now watch this. This line here is the integral. So this is the area under the curve, right? So the area between 2 and 3 is the same thing as area from minus infinity to 3 minus area from minus infinity to 2, right? Area under blue curve between 2 and 3. Is equal to area under the curve blue between minus infinity minus area under the blue curve between minus infinity and 2. Okay, do you guys agree with this statement? Right? Area under the blue curve between 2 and 3 is the same because the curve is non-negative, right? It's the same thing as area under the blue curve between minus infinity and 3 minus the area under the blue curve between minus infinity and 2. Right? Now, I'm going to put in another word. Integral of PDF between 2 and 3 is equal to CDF 3, because CDF accumulates from minus infinity, minus CDF 2. Okay, these two are exactly the same statement. Okay, this is a statement that this is this descriptive statement, right? So this could be any function. It could be mathematically drawn. It may not be mathematically drawn. It could be hand drawn. The point is that as long as you promise me that the area under the curve goes to 1 at plus infinity. The area between 2 and 3 under this curve is the same thing as the area from minus infinity to 3 minus area from minus infinity to 2, this height. So this area here is equal to this height. That is true of any probability distribution function. Now, because I drew this mathematically, this blue curve, I use this mathematical function. I also know that integral of PDF is CDF. So the mathematical function, the yellow one, is also mathematical. Now, let me see if this is true. Okay, so this is the number I want. Let me see if this is true. CDF of this at, what is it? Number 3 minus 2. Okay, well, see, I have to make numerical, right? Same number. This is what I want. Graphically, is the area under the curve 2 and 3. So it's an integral between this and that. Now I can make it even more confusing. Integrate, right? PDF x between 2 and 3. Yeah, same number. So this is asking Mathematica, if x is a normal distribution, what's the probability it is between 0, 2, and 3? Okay, let's make it 2.5, so you don't get fixated with the number 3. Say 1.2 and 2.5. That's the number, right? That's the same thing as the area under the curve. The same thing as the area under the curve when I integrate from 1.2 to 2.5. And that's the same thing as the CDF at 2.5 and 1.2. Right? You guys see that? So back to here. Why do I need integral calculus? The first reason you need integral calculus is because integral calculus is what connects PDF and CDF. Okay? Integral calculus is what links PDF and CDF. Now, so in general case, integral okay. Now, so we have differential calculus and integral calculus. I'm going to stick this in between now. Wait, first of all, are you okay with differential calculus? Okay, let me say it again. I don't care what it is. I don't care what the function you're working with. Okay. This is your function. Okay. This is your f. If you want to take the slope, you have to take the derivative. Okay. If you want the area, you have to take the integral. Okay. So let me write. Think of speed, distance, speed, time. Okay. If you drive at constant speed, okay, if you drive at speed, okay, speed is equal to distance times time, and okay, oh, sorry, distance divided by time, and distance is equal to speed times time, right? That's easy, right? That's the speed. Okay. Now you drive at variable speed. So you drive at s of t. Okay. Okay. Think of distance d of t, speed s of t, and time t. Okay. If you drive at constant speed, s of t is equal to s. Okay. Distance, speed is equal to distance times time. Distance equal to speed times time. But now you drive at variable speed. So now speed is equal to differentiation of d of t with respect to t. In Mathematica, d this is bad. I should use the IFT. Okay, let's use that. Okay, think of, okay, I'm just going to use the full name. Okay, sorry. Time, except time. Time is only one that yeah. If you drive at constant speed, speed t okay. You drive at constant speed, this is what you get. But if you drive at variable speed, okay, speed of t is equal to differentiation of distance of t with respect to time. In Mathematica, speed of t equal to d. Now this d for differential. F1. Okay. Mathematica use the word derivative. Okay, derivative. Because it's used so many times, they just use the word d. Okay. So d of speed of t. So you have some kind of mathematical function of speed. So d. Okay. Now, on the other hand, yeah, distance t is equal to integration of speed with respect to time. Okay. Which in Mathematica Okay, distance t, okay, distance t equal to integrate, okay, speed t from beginning to end. Okay, so why calculus? Calculus allows you analyze quantity of change. This is a general statement. As how quantity change. Okay? Differential, in particular, differential calculus allows you to calculate the rate of change, whereas integral calculus allows you to calculate accumulated change given. Okay. That's it. Now, for it so happens that, okay, derivative of CDF is equal to PDF, and PD integration of CDF if QCDF. So you can think of PDF as accumulating probability. Okay. For a special function PDF in probability class. Okay. So why calculus? Because you analyze things that change. Okay. Now, how about data analytics? Data analytics. Well, let me tell you this. Okay. Let's consider two kind of people. Most data analytics, you want to study y as a function of x, where you get x from data, also y from data. Okay. Think of that as a data scientist. Okay. Think of engineer, say mechanical engineer. Y is f of x, where you focus on the function something like this: dynamic behavior of y as t changes. So it's very different, right? So normally in data scientists, we're trying to say that how do you get y? How do you get economic growth? You get economic growth from investment. Okay? So you have to kind of think of this as output, input, where you get output from data, and so input from data. In engineer, you get some kind of behavior Okay, when you focus on dynamic behavior as time change. Okay. Here is fine. So it's very different. However, consider two professions. It's clear that mechanical engineer needs calculus, right? Because you want to know the total behavior. Okay, you want to know how behavior changes over time and blah, blah, blah. How about data scientists? Data scientists. Well, you can think of it this way. What if, but what about data scientists? Okay. Well, you can think of output as dynamically dependent on input. And then you can answer two kind of questions. If I knew input, can I predict output? Okay. So basically you want to know F. F. And derivative helps. Okay. Or you can answer the other kind of question. If I want the best maximum output, which input can value do I want to expect? Okay. So those are the two questions you ask. Few questions to answer. Well, if you think about it, if you want maximum output, okay, then that means what? As you change input, output changes. In particular, increases. Okay. Best output cannot increase anymore. Therefore, you can associate best output with F with zero slope. Hence, okay. So this is why it comes to you. Okay. Now think. Okay. You want to know predict output, even input. So you need to know F. So understanding rate of change is just going to help. But not only that, sometimes you want maximum output. So how do you say you get this is the maximum output you can get? When you say that this is the most output you can get, it means that even if you add more input, you can't get any more output out of it. It kind of maxed out. What it means is this. What it means is that this is your input. This is your output. And as you increase the input, you get more output. But at some point, you add the maximum. In fact, you can add more input and make it worse. So how do you find this point? You get the zero slope. So this is why differential calculus comes in. This is how differential calculus comes in. It solves your optimization problem. But I'm not so clear why is it that if I want to know just the output, how do I do this? How does calculus help? Well, don't apply derivative calculus on f. Instead, consider a different function. Call that function h. That function is the performance of your prediction. You want the maximum accuracy, i.e., right? i.e. what? i.e. h is highest, i.e. zero slope. But zero slope with respect to what? Now, this is a little bit tricky. Okay. In an engineering or in a problem optimization, again, leading back to what we were talking about, that you can imagine that you have a choice to vary your input, okay, and you want to have the one that's best. Instead of having this being input, I'm going to draw the same picture. I'm going to draw this thing called model coefficient. It's some number that drives your machine learning model. And this is your accuracy. Maybe if you have some kind of function that looks like this. Now in life will be harder than this. What is the job of your data scientist? Your data scientist is to choose the model. That model comes with coefficient. Once you choose a model, you have this line. But you choose the coefficient anywhere on this line. Obviously, you're going to choose this. So same here. You want to get the maximum accuracy. It's the same thing as trying to maximize this function. So that's why calculus comes in. This is why calculus, differential calculus, this is how differential calculus comes in. It helps you minimize or maximize your prediction accuracy. Okay, so that's why you need calculus. Now, this class I intended to be, well, I was going to say philosophical. It's not really philosophical, but you can learn the mechanic of linear algebra. Okay, and in fact, there are whole classes on YouTube and everything about linear algebra. You can also learn, and in fact, I sent you a very good one on linear algebra. You can also learn the mechanics of calculus. And some of you did that in high school. Some of you are doing it now as a refresh. Some of you are maybe taking brilliant.org refresher. Okay. What I'm saying is that Mathematica can do linear algebra and calculus for you. That's not the problem. That's not a problem. Okay, it's been done for you. For most of the problem that you're going to run into in life, you can do this. You can you know, you can go to reference page in Mathematica. Okay. And there'll be a whole things about calculus and whole thing about calculus and differentiation, you know. You can do all that. Okay. So even though I've shown you some example using Mathematica, that's not the key message of today. Okay, see the D, differentiate, integrate, all this. This is all in here. It's all in here. Solve all this in here. Okay. Same with if linear system, linear algebra. Okay, it's all in here. Okay, inverse, linear, determinant, all kind of stuff. Matrix, basic matrix operation, matrix, all kind of stuff. Okay, it's all in here. But the message is why is it that you need linear algebra and calculus so much? Okay, and that's the key message. So today it's not, yeah, it is a review, but I want you to also get the intuition of why is it that you have to work with this thing. Okay, you work with linear algebra. For those reasons, you have to manipulate a whole bunch of numbers at once. You solve linear equation, and again, don't worry. Mathematica will do it for you. Do the actual calculation for you. Your job here is to learn why is it that you need it. Okay, so this is an example, and data analytics techniques, and in the future class we'll go a lot more into machine learning and statistical method, and you will see that it requires so much of matrix manipulation. That's why you will need linear algebra. In particular, I'm going to list the topics. Okay, matrix multiplication, dot product, okay, determinant, matrix inverse. Now matrix inverse is like solving system of equation. Okay? So and finally, and the last one that you are going to need, which I haven't covered here, is called eigen system decomposition. Eigenvalue decomposition. Now, this thing you have done, determinant, I show you a little bit of that. Matrix inverse is a more it's more application on determinant. Once you determine that the problem can be solved, you use matrix inverse, can be solved. Does system of equation have unique solution? If so, use matrix inverse to solve. Okay, so I talked about this today. I didn't talk about this, and I certainly haven't talked about this. But this is another thing that we will come back to. But there's no point talking about it just yet. Well, there's some point talking about this yet, but you will see the idea when you see later, which you will see later under topic principal component. Yeah, I'm just, you see later, much later. So that's why you need linear algebra. Why do you need calculus? Why you need the calculus regarding how quantity change. Okay. Over time, or as a function of input. Okay. If the world stands still, you don't need calculus. Eventually, you don't need calculus. Okay. If input changes proportional to output. Oh, if output in direct constant proportion to input, we also calculus. Okay. Differential calculus in particular differential calculus allows you to calculate rate of change. In particular, integral allows you to calculate cumulative change. Okay. Think of that. That's it. So you need calculus, first of all, because it lives inside statistics. And also because this is the kind of question you'll be answering. Now, obviously, engineer, needs calculus. But what about you? What about you? What about data scientists or analysts? You can think of two problems. Yeah. This is how calculus comes in. It helps you maximize there. So I have given you 5 reasons for calculus. Actually, this should be like 1.1a and 1b, but that's okay. So I've given you 9 reasons to live, basically. Okay. So these are the 9 reasons that you want to be understanding linear algebra and calculus. These two are quite important. Save that. Now, as usual, I will give you I need to save this. Do you guys want this as well? The kind of class notes?
Sure, we want it that way.
I'll call it miscellaneous note today. Okay. But throw it away. But the key note you need is this guy. This one here. Linear algebra and elementary calculus. Okay. So before I forget, let me just go ahead and add this right now. Now. Work. So you need this. I'll just throw everything at you, I guess. Side note, yeah, you need side note. You need this. You need linear algebra and this note. Okay, so you have all that. Now, you guys see this, right? Now, raise your hand. How many of you could not load it? Because we would use it at the beginning of next class. Okay, so So we are a bit like one class behind, I think. Okay. So next week, I'll cover item set and clustering. Okay. You need this data set to do item set. Okay. Yeah, these are things I don't really need. Okay, but you guys have it from last class, I think. Okay, good. Now, conceptually today, I guess I could give you some homework, but it's more conceptual in the sense that today I want you to understand why you need linear algebra, and not only why, but where. Okay, so as you go to data analytics class, there'll be situation where you say, okay, well, now this is where you turn to linear algebra. Now this is your turn to calculus. But definitely, at the very least, this connection between calculus and probability statistics, this is something that I don't know if it was taught to you in class last year, but it's very important. Okay, so maybe in Excel or something, you can look up the PDF or CDF without knowing that one is the derivative and one is the integration. Derivative, by the way, the act of taking derivatives is called differentiation. Okay, maybe I should put something like this. Okay. Yeah, that's it. You integrate this mathematica. Integrate PDF. There. Okay. So this thing is what you want, probability of x, where x has distribution f, but in fact you calculate the PDF function. Yeah, so you write this or f. Okay, but normally I should put something like this just to make sure that it has all kind of parameter, because you can't just write some f, and you have to write some parameter. Integrate PDF, and you write something like normal distribution mu sigma, right? Something like that. Okay. Now, normal distribution is something you should be comfortable with. So you see that a lot. Mu is the mean, right? Sigma is the standard deviation. This just gives you the PDF of x. This is the blue curve. Integrate gives you the yellow curve between A and B, right? It's the same thing as what? CDF B minus A. This one I want you to remember. Now, in general case, right, it's not PDF and CDF, but for probability class, okay, I'll send you this one later. Yeah, I'll send it right now. Okay, let me erase the old one. Hold on. Okay. Okay, Kap. So again, I want you to think about it. I want you to go back and watch the calculus video that I sent. When did I send that? It's 3 blue, 1 brown. You should have it. Oh, I'm sorry. นัดยังมีอยู่ใช่ปะพี่เซ็นไปใช่ไหมไอ้
ครับ
Yeah. Okay. It's in the back.
Okay.
Yeah. Linear algebra, 3 blue, 1 brown. You also have essence of calculus. So between here and here, you have the mechanics and the intuition of the operation. The intuition I gave you today is not about mathematical operation necessarily, but it's about why and how and where and when you would need that as part of data analytics. Okay. So it's a bit of a review, but it's also a little bit of a preview because it's saying, yeah, you need this thing, you need differential calculus, you need linear algebra, you need certain thing, and you see it when you go to machine learning model, when you go to probability models, something like that. Okay, so the future class will refer back to how we use the mathematics of this class. Okay, so I kind of like now we are coming at some point toward midterm. Originally, I was not going to give you guys any midterm because it's kind of unlikely that you would be able to come to July, right? And online exam, we didn't quite have a platform, but now I think the engineering department of July has made exam plus software that has been tested for use with the medical students. So we might have a midterm if that system works okay. But and that, you know, obviously it's gonna give you guys individually randomized exam. So you know your problem one would not be the same thing as the next guy, and the value would not be the same, and blah blah blah. And because some of this you can search online, I think the software kind of locks your screen or something like that. So you can't really line somebody else, you know, like while you're doing the exam, you can't pop up another screen to do the line or Wikipedia or something like that. I think that's how the software works, but it still requires some kind of visual proctoring. So what might happen is this. Peanut, and I think Peanut might be able to explain this later. You would be taking the exam on Exam Plus portal that will be assigned to you. Like each one of you would have an individual portal, and that would synchronize with the exam database because you won't have the same question, obviously. It will kind of lock your screen from accessing other information or chatting with your friends or whatever. In the meantime, you would use your iPhone or your mobile, your Android phone, to set up sort of like on the side to get the view of you and your laptop. I think that's how it's going to work. Okay, so you have your iPhone. So let me stop sharing. Your iPhone would be kind of like on the side here, and then it would show your screen, your keyboard, your face, your hand, I guess. And then you would be working on an Exam Plus platform. And this Exam Plus platform, again, randomize the questions and answer and kind of locks your program. And I think, if not in this version, but in other version, it allows the proctor to randomly get a screenshot of your students. The reason they can't get, you know, continuous screenshot of everyone is because it takes too much bandwidth. Okay, so it's going to rely on like a human proctor or an algorithm to randomly, you know, maybe like this minute would take this guy's screenshot. 5 minutes later, somebody else come back or something. It'll be some kind of randomized because you can't, as far as I know, it'll take too much bandwidth to actually upstream everybody's screen. Okay, but that's what the Zoom telephone. So you would not be using your Zoom on your laptop. You'll be using the laptop to do the exam, and the Zoom you would use your phone, use your iPhone or Android to access Zoom, and that Zoom would do like what you do now, except it will be a side view. It wouldn't be a frontal view. Does that make any sense? Okay, so they're rolling this out to, I guess, not just our faculty but every school as well. But apparently they've been using it with the medical students already. It accommodates. There's some limitation. For example, it can do true and false. Obviously, that's quite easy. It can do multiple choice. It can do text input. So I can ask you exam question, like an open question, and gives you a block, maybe 5-6 different lines for you to answer to type in, which is nice because then we don't have to worry about your handwriting. But I think what it does not allow you to do is to submit something else. In other words, if I want to give you an exam that asks you to write a little Mathematica snippet, just a little code, to do something and submit it at the end of the exam period, I don't think that's possible. I think you can draw a picture, you can type, but I don't think you can write Mathematica and then submit it. I think that's the limitation. One of it, I think, has to do with the fact that once you get onto this platform, it's supposed to lock you from opening any other application. Mathematica is an application, so that's not going to be allowed, I think, which is okay. Okay, we're going to have plenty of example where you're going to have a little bit like previously, where you hand in Mathematica workbook at the end of the class or soon after. Okay, but today no class. I'm not quite sure when the exam period is. I think it would probably be in October. Okay,นัดรู้หรือยังเขาประกาศยัง? That week is a free week. In other words, if we don't have exam, we can't have class anyway. So it's like Chulalongkorn has locked that week for no instruction, so we can't meet on that class anyway. Again, it probably won't be me. It'll be some proctor who randomly looks at your screenshot and also your Zoom video. นัดรู้ไหมวันexamวันไหน? Okay, we might as well stop the video, but
Okay.